Being the mediator of the electromagnetic interaction, the photon can only interact directly with electrically charged particles such as electron, positron, proton, etc. The interaction between charged particles and photons occurs via electromagnetic processes such as photon emission. For instance, an electron can dive into a lower atomic level by emitting a gamma, or photon absorption, which is the reverse process of photon emission where an electron absorbs a gamma and jumps to an upper atomic level. Note that the photon being a neutral elementary particle, it cannot interact directly with another photon. In addition to the two basic electromagnetic processes described above, QFT, or more precisely quantum electrodynamics, QED, which is the quantum field theory for electromagnetic interaction, predicts other basic processes. The first one is when a photon annihilates into an electron and a positron. Due to energy conservation, the photon must have an energy of at least 2 mc². This process is called electron-positron pair creation. This figure shows several tracks associated with pair productions in a cloud chamber. Because of the different sign of their charges, the electron and the positron form two similar tracks rotating in different directions in the external magnetic field. Before the pair is produced, there is no track because the photon, gamma particle, is neutral. As an exercise, give an interpretation to some of the tracks in this figure. Similarly, we expect the reverse process to happen when a positron and an electron annihilate to produce a gamma. However, this process can only occur with the production of at least 2 gammas in the final state. This process is called pair annihilation. To see why pair annihilation cannot occur with only 1 gamma in the final state, we need to invoke energy momentum conservation. In the center of mass, the total momentum is by definition 0. If only 1 photon was emitted, it will carry a momentum different than 0, and the total momentum would not be conserved. As a result, at least 2 photons have to be emitted back to back in the center of mass frame. Note that the same arguments apply to the pair creation discussed before. A single photon in the vacuum cannot create a pair electron-positron because of energy momentum conservation. This process can only happen in the vicinity of another particle, or more usually, an atom. The corresponding equation for the reaction is: the structure of the atom is unchanged, but its energy and momentum are modified to account for energy momentum conservation. The probability for pair annihilation is very small if the kinetic energy of the particles is important. As a result, a positron will usually slow down, for instance in a detector, before it forms a positronium, bound electron-positron state, which decays with 2 gammas of 500 keV, carrying the mass energy of the positron and of the electron. As exercises show that a photon in the vacuum cannot create an electron-positron pair, and show that an electron in the vacuum cannot emit a gamma. The above processes are not allowed with free particles in the vacuum because of energy momentum conservation. All conservation laws like energy, momentum, angular momentum, charge, etc. apply between initial and final states. Consider the reaction with 2 particles in the entrance channel and 2 other particles in the exit channel. The conservation of energy and momentum implies the conservation of the electric charge gives. The conservation of angular momentum is slightly more complicated to express due to the fact that the particles carry an intrinsic angular momentum or a spin s, which adds up to the orbital angular momentum L between the particles. The electron is the lightest of a family of 3 charged leptons. The two others are the muon and the tau. Unlike the electron, which is stable, these particles have a short lifetime. They have the same charge as the electron. The decay process of the tau and of the muon occurs via the weak interaction, which we will discuss later after introducing the strong interaction.